All right. So I'm going to start out like a real mathematician uh, with this commutative diagram, this just explaining the concept of equivariance. So equivariance just means that you have some kind of object or a function on some kind of object, which it can suffer two types of transformations. One of the transformations is denoted in the here by phi, which is this mapping from one space to another. And the other transformation, denoted by the t by t of g, is more like an internal transformation corresponding to the action of a group. In our case, typically some kind of symmetry group, like rotations in space or permutations, that sort of thing. And an equivariance just means that this phi transformation commutes, or more generally intertwines, with this group action. So what that means is that if you take your object and then you let the group do its thing to it first, and then you apply the phi mapping, then you're going to get exactly the same answer as if you applied the phi mapping to the original object, and then the transformation according to the group happens in the transformed space. So of course, in our context, this phi is going to be the whole neural network. So we're going to be learning something about physics, and what we were trying to enforce is that something needs to be invariant with respect to, say, changes of coordinate system in your space, or it needs to be equivariant in the sense that, say, you're learning a vector valued quantity, everything really needs to transform as vectors. In particular, the answer needs to transform according to the same transformation as your inputs to the neural network. So equivariant neural networks are just a class of neural networks which somehow have this kind of property baked in. So this talk is going to be about how to actually achieve that, how to construct neural networks which are going to guarantee this equivariance property for you. So, of course, physical laws in general are equivariant to the symmetries of nature. So here is an example. For some reason, I decided to illustrate this with the Navier-Stokes equation, which has lots of different terms. On the left-hand side, you see essentially the force acting on the particle of fluid moving with the rest. And on the right-hand side, of course, it's affected by the gradient and the pressure. Then it's affected by viscosity and the outside forces and so on and so on. But the key thing is that each of these terms, if you just rotate your coordinate system or you rotate your experimental apparatus, then each of these terms is going to change, but it's going to change in the same way. And you can go through every term, look at the individual factors in that term, and figure out how that happens. So for example, this time derivative term du by dt, of course, that's just a vector. So if you rotate the coordinate system, then it's just going to get multiplied by the rotation matrix. Now you have this other term, this kind of convection term. Then you need to look at both the grad u part, which actually transforms in a more complicated way because it transforms like a matrix. So it is acted on both on the left and the right by the orthogonal matrix. But then when you dot that together with u itself, then one of these actions is going to get canceled out, and overall you end up with something which again just transforms as a vector. Okay, so this sort of this is like a fundamental property of nature that physical laws need to obey symmetries, and it's a kind of organizing principle of physics and consequently of the other sciences, and in fact is often a very big clue in terms of discovering new laws of nature, starting with the underlying symmetries, which we know a priori must be satisfied. A lot of the 20th century physics is kind of riffing off from this principle and extending it in more abstract and wild dimensions talking about symmetries to kind of internal symmetries of elementary particles, for example. Okay, so the question is, how do these ideas mesh with the neural networks? Because neural networks are very popular. Everybody is trying to use them for modeling physical interactions. But then how do you make the neural networks respect the same sort of symmetries? Okay. So the neural network, I want you to have something for now very simple in mind, like what you see on the right-hand side. So it's just kind of this information processing system. You have the individual units called the neurons, which communicate with each other. They're often organized in layers. What you have on the right-hand side is a fully connected network, but that does not necessarily need to be so. And in general, what happens is that each of these individual neurons, they receive inputs from the layer below, and then they do something with that to compute their output. And that something is often as simple as taking a weighted linear combination of the inputs and then applying a nonlinearity. So for our purposes, what's critical is that the operation consists of these two parts. First, a linear part, which, however, has learnable parameters. In particular, you often learn the weights with which you combine these different inputs, and then some kind of nonlinearity. Because if there was no nonlinearity, then the whole thing would be linear and kind of boring. Okay, so in this context, equivariance just means that if there's a specific way in which the inputs to the network transform, and there's a specific way that you want the output to transform, then when then these two are going to correspond. So if f in is transformed to tg of f in, where t just describes this action and g is the group element, then the output f out must transform according to t dash of corresponding to the same group element g. So say the same rotation or same permutation or something like that. By the way, I'd really appreciate it if when something is not clear or you have comments, then you would just interrupt me. I know it's a bit intimidating over Zoom. I can assure you that giving a talk over Zoom is only more intimidating. Okay, so at the kind of very mechanistic level, we just want to figure out how to make these neurons behave in this way. So and we want to figure out the rule or the behavior of individual neurons, such that when they receive these inputs f1, f2, f3, and produce the output f out, then when you transform the inputs, then the output is going to transform in a coordinated way, kind of the appropriate prescribed way that we want from them. So this is what the whole talk is going to be about. So one example where this sort of thing is critical, and an area that we have also contributed to, is learning force fields for, say, molecular dynamics simulations. So literally, that's a problem of learning a vector-valued quantity, the force on a given atom, as a function of the positions of our neighbors. It's very natural in this sort of problem to have a hierarchical decomposition of the neighborhood, kind of similar to how physics in general likes to decompose problems into the constituent parts. And then make these individual parts be our abstract kind of neurons. So this information is going to flow from the smaller parts to the larger parts, slightly larger parts, and so on and so on. And at the end of the day, it's going to tell us what the force on the central atom is. However, this whole thing needs to be equivariant. So if you rotate, if you just move around the surrounding atoms, say you rotate the whole system, then that means that the representation of each of these subsystems needs to transform correspondingly. And whatever means you have to describe the relative positions of the subsystems, that also needs to transform correctly. Because that's the only thing that's going to guarantee that what you get at the end, the force on the central atom, transforms the right way according to rotations or translations or whatever symmetry that you want to impose on the system. So one of the questions that that always comes up, and I can kind of preempt with this example, is why is this so important anyway if we have enough data? So it's true that in some cases in machine learning, the approach to dealing with symmetries is to kind of ignore them, hope for the best with saying that, well, actually, if symmetry is so important, is so and is so apparent in the data, then our magical machine learning algorithm is going to figure it out itself. I don't need to worry about how to put it in explicitly. So to some extent, this might be true. However, this molecular dynamics example is a typical case when this kind of attitude becomes very dangerous, because if you do not get the energies in your simulation exactly right, or the magnitude of the force, well, maybe that's not the end of the world. But really, if you try and build an entire molecular dynamics simulation on a force field which does not respect rotation equivariance, then the trajectories that you're going to get out are just completely crazy. So you can really it's a slightly different making an error on identifying some objects in YouTube videos with a certain probability. That's that's bad, but that's not quite as bad as violating energy conservation in a physical simulation. So if possible, I prefer simulations which actually respect the underlying principles of nature. Okay, so the natural place to start in talking about these equivariance neural networks is actually to talk about a much more standard and all the technology, which is just convolutional neural networks. So it's not possible to talk about convolutional neural networks without talking about this character on the right-hand side of the slide, because that's indeed the area where they have met the greatest success in identifying in computer vision, object recognition in particular, such as the famous problem of identifying cats in images and videos. This is not just any cat, by the way, this is NVIDIA's cat, so I need to acknowledge that. All right, so convolutional neural networks follow the same sort of feed-forward principle that I mentioned a couple of slides back, but what's special about them is that the connectivity between the different layers and the weights between the neurons and the different layers are constrained in a specific way, so that effectively what happens is that what's computed at each level of the network is just the convolution of the output of the previous layer with a learned function. So by convolution, I really mean the kind of classical signal processing notion of convolution that you see at the bottom of the slide here. Okay, so this involves two things. First of all, these convolutions tend to be spatially restricted. So it's not going to be true that every neuron in one layer is connected to every neuron in the previous layer. They're only related, they're only connected to neurons in the similar sort of spatial position, say there's a small square around each point. And in addition, the weights are shared across the entire layer. So the way that the one neuron is connected to the neuron just below it is the same as any other neuron and the neuron below it. So that rule is going to guarantee that the action of the neural of a given layer actually is a convolution. Okay, so then if this is how the neural network is set up, then the weights of the neural network really just correspond to this function that you convolve with, i.e. in signal processing language, the filter. Okay, so this simple architecture has some really fundamental consequences and is actually really critical to why convolutional neural networks have been so robustly successful, in particular at computer vision tasks. So one thing one consequence is that if you look at not just one layer, but several of these layers stacked together, and you look at how information flows, I mean, exactly what is going to influence what else in the higher layers, then you discover that automatically you have this hierarchical structure. So these, if you look at the receptive fields and the zones of influence of individual neurons and individual layers, and you stack them together, then they are going to form these pyramids. and meaning that higher up, you are going to have neurons that are sensitive to larger areas of the original image. But the previous layers are going to kind of pre-process those areas in the image for you in terms of more localized, more localized filters. So in terms of what you expect of how semantics comes through in vision, this actually is a very natural and desirable property. The other thing is that is automatically given to you by this convolutional structure is exactly equivariance. So because these weights are shared across the whole neural network, if you look at what this kind of hierarchy of filters does to one patch of an image and another patch of the image, it's going to be exactly the same. So if you take your image and just translate it, then in the second layer, the activations are going to translate exactly the same way. In the third layer, exactly the same way, and so on and so on, meaning that essentially meaning that if your task is, for example, object recognition, then you're not going to be biased towards recognizing objects in a particular part of the image. You're going to be equally good or equally bad at recognizing the same thing anywhere. Okay, so so this is translations, but you might say that, okay, translations is not everything. There are other natural symmetries of images. For example, there's symmetry with respect to rotations. So in order to encode that in your neural network, you need to do a little bit more work, because rotations are going to both kind of shuffle the pixels around in your images, and they're also going, and if your filters are directional, so if, for example, you have something that picks up on just vertical edges or horizontal edges, then it's actually going to permute these filters amongst themselves. So a neural network which also respects rotational equivariance is called a steerable neural network. And this has a long history in this notion of steerable filters has a long history in computer vision and neuroscience, but in the deep learning literature in particular, it was reintroduced by Cohen and Welling in 2017. Okay, but this is the key thing to realize, is that although these concepts are classical, they are just special cases of this general notion of equivariance, group equivariance, in this case, equivariance with respect to translations and rotations. Okay, so this is just a couple of slides stolen from Rip Fergus's paper a couple of years back on what features neural network trained on one of these standard image data sets actually picks up on. So this, what they did here is that they trained the neural network in the entire data set, and then they looked at what patches of what image patches from the original data set particular neurons respond more strongly to. And what you see is that in the first few layers of the neural network, it picks up on these relatively simple features like just edges or ridges or maybe little curves. And then in the higher levels, that kind of puts that together, puts these lower level features together into something a bit more interesting. And what's astonishing is that very early on, so here even in just the fourth layer, you're starting to see neurons which seem to be specialized to recognizing very specific things like dog faces. Okay, so the claim is that this is not the neural network's ability to do this is not independent of this convolutional kind of equivariant architecture underneath. Okay. So the talk, so this talk that I'm giving now is going to be about generalizing this to things other than just images and other than just translation and rotation in 2D, to the more interesting and slightly more abstract groups that come up in physical systems. So, right, any question? Somebody got a question? Okay. So the first concept that we're going to need for this is the notion of group representations. So I expect that this is all familiar to the mathematicians and the physicists in the audience, but not necessarily to everybody. So just to remind you, I'm going to give a very informal definition here. So to me, a group representation is a way of modeling a group in terms of matrices. Okay, so a group is in general, it's a pretty abstract object, right? It's determined, it's just a set of elements and an operation on them defined in some way. It can be something like rotations, in which it already is defined in terms of matrices, but not necessarily. So the way mathematicians talk about groups, they are like this elementary notion of structure, and in and it is and then which is, but by itself is not easy to imagine or to model. So group representation is literally just assigns a matrix to every group element, with the constraint that the matrices need to multiply the same way as the group elements do. So it's just a way of modeling the group with matrices. And the matrices can be of different sizes. So you can choose the dimensionality of your representation. You can have simple, sort of low dimensional representations, but you can also have representations in terms of very high dimensional matrices. Okay, so this correspondence, technically it's a homomorphism from the group onto the to the set of invertible, actually square complex matrices. So the reason that group representations we cannot avoid talking about group representations here, is that in practice, when a group starts doing something, as in it starts acting on our images or our molecules or something, then the way as long as that action is linear, it's kind of crazy if it's not linear, but so everybody that is in this field only considers linear actions, but the linear action itself is a group representation. So very quickly you end up talking about how these what the group representation is, how it possibly breaks down into smaller representations, and how that's going to correspond to things inside your neural network. Okay. So the thing with group representation theory is an area of math, and we're not going to be discussing it much here. But the thing about it is that it's actually a very well-developed area. So in terms of creating your neural network to respect a particular symmetry, you can just refer to the appropriate book in the library, and it's going to tell you everything you need to know about the representation of that group, like how many representations there are, what they are, how to compute them, what the relationships between them, and so on and so on. So for example, in simple cases, there's just the three-dimensional rotation group. And of course, as I said, the rotation matrices, so orthogonal matrices themselves form a representation of that group. But in fact, there is an infinite sequence of these so-called irreducible representations indexed by a number L. And as it so happens that the irreducible representation corresponding to L is going to be exactly 2L plus 1 dimensional. For the physicists in the audience, this is probably already ringing all sorts of bells with the quantum mechanics and the irreducible representations of FSU2 and SUN in general, and so on and so on. So those are all very valid and relevant connections. But you can also do the same thing even for a finite group. So for example, if you consider permutations, then the n factorial different permutations of n objects form a group called the symmetric group of order n. And the representation theory of that is also well studied. Weirdly, it turns out that the irreducible representations are then indexed by these things called Young diagrams, like consisting of putting these n boxes down and conforming to strange rules in these kind of Tetris shapes. So each Tetris shape has a corresponding irreducible representation. So if you want to do something with the symmetric group and you want to build a neural network that respects that sort of symmetry, at least formally, you need to worry about all that. Okay. So back to neural networks and equivariance. A very simple theorem is that is what I already actually mentioned just before, is that whenever you're in a situation that some layer of your neural network, or even some part of the neural network, transforms in a prescribed and linear way according to your symmetry group, then that transformation must in fact be a representation, not necessarily reducible, but a representation of the underlying group. So it must be expressible. And for now, we're only talking about a finite dimensional case. So these are finite, it's a neural, after all, it's a neural network. So you have finite dimensional vectors, you have linear operations on them, i.e. you have matrices. And of course, if you apply one transformation and another transformation, then the corresponding matrix must be the same as the product of the transformation corresponding to the matrix corresponding to the third transformation multiplied by the matrix corresponding to the second transformation. So it is a representation. So already we've somehow landed in this land of representation theory. So all that we need to figure out, so now that we've established this, all that we need to figure out is what the neuron is going to be allowed to do. So if we know that the inputs transform according to a particular representation, like row 1, and the output needs to transform according to another representation, say row 2, then what is the neuron going to be allowed to do so as to make sure that that these transformation rules are not violated? Okay, and following the way I talked about neural nets in general, we are going to be examining this in 2 parts. First, we're going to look at the linear part, and then we're going to look at the nonlinearity. Okay. Any questions at this point? Anything to clarify?
Yeah. All right. Well, maybe just before you scream on, maybe go back 1 slide and just give us an example, like I don't know, rotations of colors in space in a color wheel, or just something really simple of what the transformation is, and explain what the row and everything like that is.
Yeah, so actually, one of the most natural examples is what I started with, that is that learning something like a vector valued function for a physics application. And there the transformation, the symmetry group is the group of rotations. Okay. And so correspondingly, this row is going to, as I said, is going to be one of these sets of Wigner matrices. So in this, actually the simplest case is that internally the neural network just propagates 3-dimensional vectors, in which case the row would just be orthogonal matrices. So that's very simple, right? So what the neuron gets is a bunch of 3-dimensional vectors, and what it outputs is also a 3-dimensional vector or several 3-dimensional vectors. However, that's not quite the whole story. So there are other quantities which transform linearly with respect to rotations. In particular, if you look at the spherical harmonic expansion of something for a given L, then this vector of spherical harmonic coefficients, say you want to do like fast multiple, like actually Jason mentioned, or anything else or anything else involving or spin in physics, or anything else involving expanding things in terms of kind of rotation order, then that's going to transform according to the corresponding irreducible representation of the rotation group. So in physics applications, you really need to be mindful of what quantities are scalars, what quantities transform like spin, what quantities transform like 3-dimensional vectors, and so on and so on. So I intentionally don't want to go into actually writing down these irreducible representation matrices and so on and so on. They just involve a lot of impressive algebra, but not necessarily very intuitive. Okay. So so let's talk about this first, the linear part of the transformation. So we are going to conceive of these activations that transform according to the group actually as functions on the group, because that's exactly what happened in the convolutional neural network case, right? So what is that you have in the input or in one of the subsequent layers of a neural network, where it's just a function on this grid on R2. So it's really, if you make it continuous, it's actually a function on the plane. So what the neural network does is that it transforms one function on the other plane to another function on the other plane, and so on and so on. So most generally, we can look at the activations in this group equivariant neural network similarly as a function on the group, or the details will come a bit later. Actually, on what is called a homogeneous space or a quotient space, the group divided by some subgroup of it. Okay, and then and we saw that in the case of CNNs, what the network actually implements in each layer is just convolution with a learned filter. Now it turns out that there's a generalization of the notion of convolution to groups as well, even non-commutative groups, which looks exactly the way that you would expect it to look. So you can see on the right-hand side that instead of x minus v, you just evaluate f. You just have two group elements, u and v, and you evaluate f at u times v inverse. Okay, because that's like the analog of minus on a general group. Okay, and integration, it turns out that there's a natural measure to integrate with respect to on at least compact groups called the Haar measure. So that's so that dilemma is taken out of the picture as well. Okay, so the first kind of reassuring kind of anchor in this whole field is this theorem that actually we proved a couple of years ago, which says that whenever you have a equivariant network of the simple kind of feed-forward type, which has these interwoven linear and nonlinear operations, then the linear operation must in fact be one of these generalized group convolutions. So this is a very nice that this whole idea of convolutions just generalizes directly, in this case, to any compact group. So that covers things like rotation groups and other compact Lie groups, as well as any finite group like the permutation group. And similarly to the CNN case, this means that what you can learn in your neural network are going to be these filters, which now are functions on the group. But never mind, it's something that's a well-defined quantity, and you can learn it, and this whole architecture is going to guarantee equivariance for you. All right, so lest this be a little bit too abstract at this point, I can give you a specific example, both of the group action and the homogeneous spaces, and also what convolution means. So imagine that you want to do the same sort of thing as before in convolutional neural networks. I learned something about images, but in a way that behaves nicely with respect to translations on the images. But now the images are painted on the sphere. So this is kind of a spherical object recognition task, which actually comes up in all sorts of applied areas in robotics and elsewhere. So what is the group? The group is just the rotation group. What is the space on which the functions are defined? Well, now it's the sphere. So the sphere is not the same as the rotation group. It's one of these quotient spaces. Actually, the sphere is the rotation group divided by the SO2, so the two-dimensional rotations, it turns out. And now you want to be equivariant. We want to the full rotation group in this case. How do you achieve that? Well, of course, the way you achieve that is that you take the correlation between your input image and these filters that your network learns, which you are now allowed to move around on the surface of the sphere. And you're also allowed to rotate around its center point. Okay, so there's this natural notion of convolution or correlation on the sphere, and actually this corresponds directly to this more abstract group theoretical, the more abstract group theoretical terms that I was talking about in the previous slide. Okay. Now the other component is the nonlinearity, and what is the kind of nonlinearity that people use in the classical case and say convolutional neural networks? It's just something like a ReLU. So really, what it is, it's just the pointwise nonlinearity. You have this pre-activation, which you get from the linear which you get from the linear transformation, and you just pointwise apply some transfer function like this cutoff absolute value function to get your output and make sure that the transformation overall is nonlinear. Now, it turns out that you can do exactly the same on a group. So you just have a function on the group or on the sphere, this homogeneous space, and then you apply the ReLU to that, and then in some sense you are fine. Okay, so this is all very good, but it does have a little bit of a at least a computational drawback, and that is that what I just described requires doing all these operations on, like, it essentially requires quadrature on the group, right? So you need to define everything on the group or just on the homogeneous space or something like the sphere, and you need to compute these integrals over these weird curved spaces, and you need to apply this nonlinearity. There are lots of opportunities for numerical error to creep in, and also the whole computation is certainly not as well, doesn't exactly mesh as well with, say, graphics processor architectures as the kind of relatively pedestrian matrix and vector operations that machine learning people are used to. So the next part, which I think is maybe the most important part of the most interesting part of this whole story, is how we can actually get around all these issues simply by going to Fourier space. So now we take our poor cat, but now the cat is going to be in Fourier space. Okay. So the reason that this is all possible is because actually Fourier transformation has a direct analog on groups. And you can kind of figure out what it's going to look like just by writing down the ordinary Fourier transform and staring at it and thinking about how you would generalize it to when, instead of being on the real line or the plane or d-dimensional Euclidean space, you happen to be on a group. Okay, so this is the answer. So just like in the classical case, it's an integral over the group, according again to the standard measure, the Haar measure on the group, weighted by something. But instead of weighting by these complex exponentials, here you are weighting by, surprise, surprise, by the irreducible representations of the group. There's some noise in the background which may be bothering you, so I'm actually going to go inside. All right, sorry about that. So in so many ways, this is kind of reassuring that there's such a simple analog of Fourier transformation in groups. On the other hand, it's a little bit weird, because if you think about what's on the right-hand side, well, I just told you that these representations, these rows, are matrix-valued functions, right? So this means that these integrals are also matrix-valued. So you take, when you're on a non-commutative group, what happens is you take out, you start with a nice and honest function on the group, you do the Fourier transform, and what comes out is not a function in a group, but this bunch of matrices, like one matrix corresponding to each irreducible representation. So I admit that this is a little bit weird. On the other hand, this generalized Fourier transform still respects many of the nice properties of Fourier transformation from the classical domain. In particular, it's going to obey the convolution theorem. So I told you what convolution on the group is, and of course we know that in the classical case, the convolution is diagonalized in Fourier space, i.e., the convolution of the Fourier transform, the convolution of two functions is just the product of the Fourier transforms of the individual Fourier transforms. Now, this exact same property also holds in this non-commutative case, except what you have on the right-hand side now is, of course, matrix multiplication. So from a computational point of view, from actually having to do this in TensorFlow or something to train your neural network, this is already way more attractive to then doing that integral over the entire group, because it tells you that all that you need to do in order to compute these convolutions for the linear part of your neural network layers is just essentially multiply matrices, which these packages are actually really good at. Okay, so similarly, equivariance, which corresponds to the action of translations on a function in Fourier space, has a really nice form in Fourier space. It's just going to correspond, and then in the non-commutative case as well, it's just going to correspond to multiplying the Fourier matrices from the left by the corresponding representation matrix. Okay, so now we can rephrase our theorem for what the linear layer in the neural network is allowed to do in Fourier space, and it looks much simpler. So all that's going to tell you is that actually these activations, one way you can look at them, of course, is a function of the group or a function of the homogeneous space, but a much easier way to look at them is just these matrices, each one matrix corresponding to each of the irreducible representations, and then the way that way these are going to transform under the linear operation, what the linear operation is going to do to them is just matrix multiplication with the learned weight matrix. So this fi dash equals fi wi, that's actually what the neuron is going to be doing. This is the wi, the actual weight matrix that the neuron learns, and this is the only thing that it's allowed to do in order to guarantee that equivariance is preserved. Now, what about the nonlinearity? So previously I said that the nonlinearity has to be a pointwise function on the original group or on the original homogeneous space. So you can still do that, but now you need to realize that that's going to involve backward and forward Fourier transforms all the time, going from these matrices to the function and from the function back to the matrices. So you might or might not want to do that. In some applications, that's actually fine, but in other applications, it's always going to be a bottleneck. So you might wonder, is there any way to then have a nonlinearity in Fourier space, which is still equivariant and not entirely trivial? And if you think about it a little bit, you quickly discover that the natural thing to do is to consider tensor products. So the question is, how do tensor products of irreducible representations decompose into individually irreducible representations? Fortunately, this is a question that comes up in many other contexts and has been answered by something called the Clebsch-Gordon decomposition. This also tells you, incidentally, how to add an angular momenta of different particles together in quantum mechanics. So this is why it might be familiar to some of you. Okay, so anyway, so there is this magical transformation out there, which working it out from scratch is not trivial, but it's a fixed transformation, fixed linear transformation. You can look up the transformation coefficients, which is going to take two of these Fourier matrices transforming to specific irreducible representations, take the tensor product and decompose them into another bunch of matrices, which also transform according to individual irreducible representations. So it's a manifestly nonlinear transformation, yet it is equivariant. So this is actually what I would advocate for in using in your equivariant neural networks, because it's much neater just being able to stay purely in Fourier space and applying this linear transformation. Okay, so on the whole, I've kind of given you just a kind of the backbone of this framework for implementing equivariant neural networks for simulating your physical system. Okay, so how does this go? Well, first you start with your problem, say learning this force on the central atom in a given molecular system, and you identify the symmetry group. Okay, so that might be something as simple as just the rotation group, or you might explicitly need to consider both rotations and translations. Here, in the case of force field learning, that did not actually cause too much trouble because all the distances were relative distances anyway. So we kind of implicitly factored that by translations. But in other cases, you explicitly need to talk about translations as well. Or if you have some kind of relativistic problem, for example, you are going to be looking at, say, the Lorentz group. We actually have a paper on that where we built a neural network for classifying collision events, or these jets, in particle colliders, or when in problems which involve exchangeable particles and you need to be invariant or equivariant with respect to symmetry, you would be looking at the symmetry group, and so on and so on. So this whole list of groups that actually come up in physics, you need to look at the corresponding irreducible representations, and then you need to define the activations in the neural network in terms of these irreducible representations. So you're going to need to say that, okay, this neuron communicates with that neuron, and is going to send, three vectors transforming according to this irreducible representation, and 5 according to this irreducible representation, and so on and so on. So that is a design choice, right? Like, how are you going to capture the relevant stuff about your problem in your neural network? Okay, and then you need, the final ingredient is you need to figure out what the neuron is then going to be allowed to do, and these operations are really constrained by everything that I told you in the last 40 minutes. So you're allowed to take linear combinations of these Fourier matrices. You're allowed to column-wise concatenate them. That's fine. You're allowed to multiply them on the right by fixed or learned weight matrices. And you're allowed to do the Clebsch-Gordon product or higher order versions of the Clebsch-Gordon product. And that's everything. So this is what the design of these neural networks boils down to. And we played around with this a little bit, trying to improve performance in the force field learning problem. What we ended up with, at least last year, in our architecture called Cormorant, is on the bottom. It's just one particular way of combining pairs of information coming from pairs of atoms in terms of both the Clebsch-Gordon product and just the dot product between their activations. Okay, but clearly there's a lot of room to play around with this. All right, so actually I'm not doing so badly on time. I've got about 10 minutes. So the last part, I want to talk about how this might actually look like in software, because it is possible to just implement this. After all, this is the same old story, right? It's just a bunch of matrix operations that are differentiable and so on. It is possible to implement this in PyTorch or TensorFlow, the popular neural network libraries, and some people have done that. In particular, there's this SE3 neural network library, which you can find online, which interfaces to PyTorch. But there are fundamental limitations. So in order to be able to, so we found that, for example, this architecture that we had on the previous slide for force field learning, when in our naive PyTorch implementation, had real trouble scaling to systems with more than about 20 atoms, because essentially because it took this Clebsch-Gordon operation literally and computed these tensor product matrices and then tried to store them on the GPU, which very quickly saturated the memory, and that being the fundamental bottleneck. Okay, so an alternative is to kind of build your own. So that's what we've been doing. We've been working on a flexible C++ based framework for group equivariant neural networks for the last year or so. Okay, so this is named after another type of cat. It's called GeNet, for group equivariant neural network. Okay, so at a very high level, some of the design objectives of this framework are going to be that these group equivariant quantities, like these matrices that transform according to specifically irreducible representations, or collections of matrices which transform according to a particular combination of irreducible representations, they are kind of fundamental types. So just like a bit like the doubles and floats and so on, they are fundamental types of the library. And in particular, and it should help people write networks that actually are equivariant, because when you deal with one of these types, you're not allowed to apply operations to them, which would break the equivariance. So you can add these vectors together and so on and so on. But for example, you can't individually fiddle with the group with the elements of these in these Fourier matrices, because that would mess up equivariance. Okay. Now, the second thing is that we have efficient implementations for the relevant operations, in particular the Clebsch-Gordon product, which avoids constructing the tensor product in the first place. So it turns out that there's a lot of structure on the Clebsch-Gordon product, and just implementing directly in CUDA gives a huge saving in computational efficiency. Okay, so that already reveals that the library both has a CPU and the GPU backend. You can move back and forth between them. And the next component is actually technically most challenging, is that is the scheduling of these operations. So it's fine to write a CUDA kernel for an operation that's essential for your neural network, but really the GPU is only able to help you much if your code has a structure, or your underlying problem has a structure where the parallelism is apparent from the start. So where you really need to apply the same operation to a large number of data objects of same dimensions. And in these general equivariant neural networks, for example, in the case where you're learning something about molecules, and the structure of the computation graph itself, the structure of the neural network is itself determined by the molecule, and therefore does not follow such a simple structure as, grid upon grid in convolutional neural networks. This kind of the kind of trivial parallelism is not guaranteed at all. So then the network, this library is also going to have the ability to kind of batch together operations on the fly, and it's called dynamic batching, which means that in the background it collects operations and batches together them together in such a way as to make it easy to be executed in parallel all at once at some later time on the GPU. Yeah, of course it supports automatic differentiation like any honest neural network library, and the whole thing is in C++11. So hopefully this will also give it further performance edge. It also means that currently the only front-end interface there is to it is in C++. But it's pretty natural C++, and it meshes with the rest of the language. So you can freely mix the operations from the library with regular C++ code. So for example, this is a snippet from something that implements something like one of these something like a model for given a single layer of one of these force field learning algorithms. And you see that the code is pretty compact. So it just defines these SO3 vec and SO3 part objects as you would expect them, or like arrays of these things, and iterates through your pairs of atoms, and explicitly computes this Clebsch-Gordon product between the activations of any pair of atoms, and adds them to the activation of the new layer. And of course, as I said, the whole thing is differentiable. So this is the forward code, but the code for the reverse mode differentiation in the backward sweep to update the parameters is generated automatically. You never have to worry about gory stuff like figuring out the derivatives of the Clebsch-Gordon product and so on. Okay, so this is about it. I finished right on the dot. I'm very happy to answer questions.